are going through number 6, and we're going to try and find a calculation question. And we can see 6A says define, 6B says describe, 6C says state, blah, 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 explain. So we'd go down to number 7, which says suggest. Then all these other diagrams and stuff. So we're skipping this for now, right? We'll do it. Number 8A says now, okay, using symbols, draw a diagram to show whatever. So anyway, we'll talk about diagrams, don't worry. Now here we get to 6, we get to number D, which is, what number is this anyway? This is number 8 now, okay? We had no calculation whatsoever till we got to number 8D, which says determine the time that has passed since it was manufactured. What is it? A very old object made of wood. So here we have half-life, which we can say T half of carbon is 5,700 years. In other words, after every 5,700 years, the activity of the whatever carbon would have decreased by half. It always goes down. So this is what happens. By activity, we mean the amount of things which it shoots out from the nucleus, all right? So here we've been told that this thing here, it's made of wood with this amount of atoms. When it was manufactured, it contained this amount of atoms. So remember, half-life is what you take to reduce your activity by half, or to reduce your activity to half of what you were, right? To half of what you were at the beginning. So now, it's not only the activity that we say reduces by half. We can say when the amount of things that are inside also reduced by half. Okay? So here, what are we having now? At first, it was 1.2. Let's say when it was manufactured, it was 9.6 times 10 to the 11. Now it is 1.2 times 10 to the 11. So the first thing which we are going to do is we are going to see how many half-lives has something gone. To get half-life. Okay, so let's talk about it. Here's the thing. Let me say this, class. Remember, we are doing topics 4, 5, and 6, right? We are doing questions from topics 4, 5, and 6. In Unit 4, or from Unit 4, 5, and 6. In Unit 4, which is electricity and magnetism, that is where you actually have quite a few formulas to use, okay? This is where you actually have quite a few formulas to use. And let's put them down, all right? Let's put down these things. So I'm just going to do it. But we saw that there was no calculation on electricity anyway. So maybe I should leave that. From Unit 5 is nuclear physics. This has hardly anything. Nuclear physics from the nucleus. Here you don't have to know anything except for calculation of half-life, which you're going to learn right now as we are doing it. There is no particular formula, okay? Then here we are going to Unit 6, which is going to be space physics. So let me just put for you Unit 4, and then I put Unit 6. Remember, Unit 5 is just nice and easy, okay? It has no real calculation. We'll just talk about how we balance equations and whatever. We won't give you a formula to remember. But in here, let's talk about some things. For you start by talking about all the electrical quantities, like current. You start with current, which is the rate of flow of charge. So you must know that current is the rate of flow of charge. You must just know it, okay? We don't want you to cram anything. I mean, you must know how to get the potential difference, which is the energy per unit charge, like this. It is also the EMF. This is the new formula. Please have it. It's the energy per unit charge. The EMF is like the voltage you see at the source. That is like the supply voltage. So let's say this is 12 volts at the source of the whole thing, right? And then now when we talk about potential difference, we'll be saying if I check across one element. So let me do it. Let me show you what I mean. Let's say that if I now take across this thing here, this is now your V. Across one guy. Okay, so we'd say W is the work, which is also the energy. So this would give me, help me to find the EMF and the, so this is EMF, which is the same as voltage, only that EMF is now for the whole circuit. The energy or the work done as a charge, the energy it loses, or the work it does to move across the whole circuit, or to move around a complete circuit. And you divide by the amount of charge you had. Okay, then here we have the work done, divided by the amount of charge. But remember, is the energy transferred to a component or whatever you have. This is going to be the other thing to know, right? Potential difference and EMF. Then we talk about resistance, right? We talk about resistance. And for here, you should remember that V is IR. This is called Ohm's law, okay? And we can make resistance the subject and it'll be fine. Remember, V is IR. When I have resistance and current and voltage, when I want the relationship between the three of them to find whatever I want, I'll be doing this. This is the one you got to know for resistance, right? Then we talk about electrical energy. Now let's talk about electrical energy. The E, which is equal to VIT. You must know this, that E is equal to VIT for electrical energy. And then we go to electrical power. Electrical power is VI. And we also say that electrical power, we're talking about electrical power here. We can also use the one from mechanical power, where power was work done over time taken. But remember, this one is going to be electrical work over the time taken. So it's like we can say power is the energy transferred divided by the time taken. But remember, we are talking about electricity, so it will be some electrical thing. Okay, then now we can talk about the calculations which we learned from circuits, right? From circuits, you must remember that current is the same in series, and you must remember that voltage is the same in parallel. So when we have two parallel things, voltage is going to be the same. When we have two things that are in series, the current is going to be the same. Current is the same in series, but in series, voltage is shared in series. So because voltage is shared in series, when we can talk about us having, let's say we have a source like this, okay, and then we're going to have a resistor, and we have another resistor here, and now we want to find out, okay, how much, let's go, this is R1, this is R2, they have different resistances. We want to know, okay, this was the EMF. How much of the EMF comes here to be V for V2, and then how much of it comes here to be V1? So because we know that voltage is shared in series, so how much comes there? We call it the potential divider rule. We use what we call the potential divider rule, right? And potential divider rule just says, if you say R1 over R2, this is going to be equal to V1 over V2. Are we together? R1 over R2 is equal to V1 over V2. And remember, when I want the EMF or the voltage of the source, I'll just now say, okay, so here you'd make whatever you want the subject. Let's say I wanted V2. I would now say R2 over R1 is V2 over V1. That's the potential divider rule. But remember that the total EMF is just going to be V1 plus V2. If you wanted it at the end, the EMF, the voltage of the source, the total V. Okay, the voltage of the source. Remember that. Remember that. Are we together? Now, let's talk about one more thing, which is how we get resistances when things are in series. To get the total here, when things are in series, it will be R1 plus R2. This is for series combination. Now, when things are in parallel, we say RT is equal to R1 times R2 over R1 plus R2. This is when we have two things. And this is for parallel. When you have two resistors and you want to get the total resistance in parallel. If you have more than two, you would use this. 1 over RT will be now 1 over R1 plus 1 over R2 plus 1 over R3. Okay, remember this one. And you are done. Can you imagine? There's one more thing which you need to know, and this is from electromagnetism. Remember, here we're dealing with electrical quantities. Then here we are now talking about circuits. Okay, electrical circuits. The electrical quantities are the powers, the currents, the whatever, the things, words you meet. And then now finally what you gotta know in electricity, what is the last thing I gotta know when I have all this? The last thing you gotta know is in electromagnetism, which is, remember, the relationship between electricity and magnetism. When we talk about the transformer, the motor, and all this, the only formulas you gotta know are for the transformer. So when we have a transformer now, where am I gonna put it? Let me put it here. This is still unit 4, right? This is still unit 4. Basically, the thing to remember about a transformer is that it looks like this. Then it is going to have some windings here and some windings here. And this we call the primary side, okay? And then the other side we call the secondary side. So now you must know just these two. Is the relationship between voltage and the number of turns of this wire. Remember, you are turning a wire, you're making it go round and round. And so it's the relationship between number of turns and voltage. We say that voltage at the secondary over voltage at the primary is equal to number of turns at the secondary over number of turns at the primary. So what you do with voltage is what you do with number of turns. If you say voltage at the primary over voltage of the secondary, this is equal to number of turns at the primary over number of turns of the secondary at the secondary. So this is what you got to know. It's the same as what? As this one. And what did we call this? Do you remember what we called it? What did we call it? The potential divider. So this is the potential divider rule. Okay, it's the relationship between R and V. R and V for potential divider. It's R and V. Remember that. But for transformers, it's now voltage and the number of turns. And are we done? No. You must just know one more thing. the power at the primary should be the same as the power at the secondary for an ideal transformer. So now if you see them say ideal, which is the one they would give you, you'd now say the power, remember power is VI. So we're going to say V primary times I primary is equal to the power at the secondary, which is V secondary times I secondary. Remember this. And then that's the other formula we're going to use. And we would be done. So this is for our unit 4. Now we just go to the last thing, which is the thing we need for unit 6. Okay? Now for this unit, there's some things that I just need you to know. Okay, maybe let me do it in its own video. So let's talk about unit 6 in the next video, and then we'll see how it goes. Goodbye for now.